Hello, guys. You're welcome to the second part of the lecture on introductory abstract algebra. In this lesson, I'll make a couple of videos and we are going to look at groups. Okay, so we are going to focus on groups. I'll give an introduction and a sort of a motivation for groups, some examples, and then later on we'll look at theorems on groups, and then some specific examples, or if you like, unfamiliar examples of groups of permutations. Okay, so that is the plan. So what do we need these groups for? Well, recall that when you were in first grade, or maybe many years ago, after you learned a simple concept of, say, addition and multiplication in basic or elementary algebra, well, the next thing on the agenda was for you to learn how to solve linear equations, right? Solve problems with the binary operations that you learned, addition and multiplication. For example, you were asked to solve a linear equation, simple linear equation like this, right? M plus x equals n, or m times x equals n, solve for x, right? And you're familiar with the joke that find x, right? So you were asked to solve this one to find x. Well, in the linear additive case, there's always a solution. There's always a numerical solution to this. Okay, you can always solve this for x. In the case of the multiplicative one, well, you can still solve it for x if m is not equal to 0. Of course, m is not 0. Otherwise, m is 0. Okay, so in this simple linear equations, we're able to solve for the value of x. So in fact, a good motivation for, let's say, the negative numbers, note that here we're just using addition, right? A good motivation for the negative numbers is actually the need to be able to solve linear equations like this, right? Or 7 plus x equals 3, all right? In a similar manner, right? The need to solve this equation, right, is a motivation for the rational numbers, right? In other words, to solve this, you need to introduce a rational number. Okay, so good. So this is all about introduction. Okay. Now, in the same way that many years ago you were asked to solve, say, 7 plus x equals 3. Now we'll like to be able to solve, let's say, any linear equation for any binary operation, not just addition or multiplication, right? For any binary operation, we would like to solve a linear equation. Now, but if you just choose any binary operation, it is not always possible to solve the linear equation, all right? Unlike the addition and multiplication that we looked at. So in general, it's not always possible. So the question is, under what conditions can I specifically say that I'll be able to solve a linear equation, whether additive or multiplicative linear equation? Okay, so it will be important for mathematicians to be able to tell that given this linear equation, I'll be able to solve it based on these conditions that it satisfies, if you like. Okay, so that is the main idea of groups. When we get to defining groups, you understand why. Okay, so to start with, I'm going to do some simple examples just to illustrate the need for these axioms or these rules, okay, that govern what a group is. We'll come to that. So to start with, we are going to look at an equation like this: 7 plus x equals 3 under the set of integers, okay? And then to be able to extract or abstract or to derive the essential concepts that we actually need to solve this, okay? I know that you guys can solve this. You can solve this maybe in class 5, grade 5 or grade 6. You already know how to solve this. So the point is not how to solve it. The point is, what are some of the essential concepts that are required to enable you to solve a linear equation of this? And then after we've done that, we'll look at the multiplicative one, okay? So, but the caveat is this: to solve this, we want to solve this based on only a single operation, addition. Okay, we don't want to introduce subtraction. We don't want to introduce multiplication. To solve this linear equation, this particular one under integers, we want to be able to solve it using only this single binary operation of addition. Okay, so I should be able to pick any number from the set of integers to be able to help me to solve this. Okay, so that is the main caveat. Okay, so let's look at this example and see some of the things, the concepts that we apply in solving it. So I have 7 plus x equals 3, right? This is given to you. Okay, now what I can do is that I can group this, and then I add to the left-hand side of this, I add -7, right? And then to the left-hand side of this, I add -7. So all I've done is add -7 to each of the expressions on the left and right. Okay, now under addition, we know that addition under integers is associative. So because it's associative, we can actually regroup this to get that, right? And it's equal to the right-hand side. Good. And then we add these terms here, -7 plus 7, of course, is 0. I have 0 plus x equals -7 plus 3, okay? And then I know that in the set of integers, if I add any number to 0, I get what? I get back the number, okay? So 0 plus x gives me x, of course, and this is equal to -7 plus 3. -7 plus 3, of course, is -4. Okay, so we have shown that -4 here is the only possibility, if you like, for a solution to this linear equation. But really, that is not our focus. Our focus is that, look at the steps that we used to arrive at this. What are some of the concepts that we applied? To be able to solve it, first, we introduced the negative of this number here, 7. So what it means is that to solve this, it is important that within the sets that I'm considering, there should be the negative or the inverse in terms of, in the case of addition, the negative of this number must exist within the set that I'm looking at. So that is important. Later on, we'll see that this negative number here is called the inverse in general, okay? It is also important that the operator or the binary operation that I'm using, it should be associative. So we also need the associative law. So that is important to note. In addition to that, within the set, there has to be an element such that when I add any number or any element from that set to it, I get back the same number. So I need, in this case, I need a 0. Later, we'll see that this 0 will be called an identity, okay? So you need 0, such that if I add it to x, I get x back. So these are the 3, if you like, main concepts that we applied. We applied the fact that I need the negative of 7 to help me solve it. I also need the associative law so that I can regroup this, okay? And I also need 0, okay, to be present so that whenever I add 0 to any number in the set, I get back the number, okay? So remember this. Now I'm going to do that of multiplication, and then you will notice that we need these 3 essential ingredients, if you like, in order to be able to solve a linear equation, whether it's multiplicative or additive. So let's take a look at 3x equals 5 in the set of rational numbers, okay? So if I take the rational numbers, what it means is that to solve this, I can basically pick any rational number and apply it, okay, to enable me solve it. So again, let's look at the steps. 3x equals 5 is given to me. To solve it, I can multiply on the left-hand side of this by 1/3. I can multiply here by 1/3, right? So that is what we have here. Really computational. I haven't done anything else. Good. Now, because multiplication under rational numbers is associative, I can regroup this and write it as 1/3 times 3 multiplied by x. This is still the same as that. This is fine. Okay, so I applied associativity. Also, if I multiply 1/3 times 3, I get 1. So I have 1 multiplied by x, and that is equal to the right-hand side. Well, One is such that whenever I multiply any number by it, I get the number back, right? So 1 times x gives me x, which is equal to, of course, 5/3. So again, notice that the 3 essential ingredients or steps or concepts that we applied was the fact that to solve this, because I have a 3 here, I need to have the number 1/3. The inverse or the reciprocal of it must be present in the set. Okay. Again, in the case of multiplication, you will see that this is the inverse of the number 3. So you need an inverse. Okay. You also need associativity. And then you also need, in the case of multiplication, you also need this number 1 to be present so that whenever I operate any element on 1, I get back the number, right? So 1 times x will give me x. So 1 has to be present. So I need the inverse of this number here. In general, I need the inverse of every number in the set of rational numbers, okay? So, and I also need 1. So again, you have the 3 ingredients: inverse, associativity, and identity. In the case of multiplication, this one here becomes the identity. You see? So these are the 3 things that enable us to solve this, to arrive at this answer or this solution. So I'm going to summarize here. Okay. So what that means is that in general, all right, given a binary operation and a linear equation with that binary operation, you'll be able to solve that equation if you have these 3 ingredients present. Okay. And the first ingredient is that you need an element E, okay, such that when you multiply any number by that element, you get the number back. Okay. In the case of the addition, right? In the case of the additive linear equation, E there was 0. Okay, so that whenever I add 0 to any number, I get the number back. In the case of the multiplicative one, E was 1. Okay. And then you also need the presence of an element, right? Say, call it A prime, all right? Such that if I multiply it by A, I get back the identity element, all right? So this was like the inverse that we needed. Okay, so you need the presence of this kind of inverse. In the case of the additive one, this was like -7. And in the case of the multiplicative one, that was 1/3. Okay, so these are the things you need so that -7 plus 7 will give you the identity which is 0 in the case of the addition. Okay, so you need these 2. Apart from these 2, you also need the associativity law. The rest of the procedure was basically computations, right? 3/5, if you like, 0 plus some number. The rest are basically computational. So basically the essential steps are the presence of that inverse, the identity, and the associativity law. Those were the ones we used. Okay, so in other words, remember that I'm just introducing, this is just an introduction and motivation. In other words, if I have a binary structure, in other words, a binary structure is basically a set plus a binary operation. If I have a set and a binary operation, and I have associativity, right? If the operation is associative, if I have an identity element in the set, and if every element has an inverse, all right, in the set, then this structure is called a group. Okay, so basically that is a group. And why is that important? If it's a group, then we know that we have these ingredients that helps us to be able to solve a linear equation, whether it's additive or multiplicative or whatever the operation is. Okay, these 3 ingredients are important. So this brings us to the formal definition of a group. Okay, and in order to actually reduce my the time, well, I'll go through the definition of a group and some examples, and then we'll bring that to the end and then go to the next one. Okay, so this brings us to a formal definition of what a group is. So suppose that G is a set and star here is a binary operation on the set G. And then suppose star is associative, and also suppose that there is an element E in G such that X, right? X here is an element in G times E star X is equal to X. right? For every x in G. And also suppose there is x in G such that you can find this element x inverse or x to the negative 1, all right? Also in G such that x star x inverse equals x inverse times or star x equals E. If these three, right, given this, if these three conditions or ingredients are satisfied, then the set G together with the binary operation star is called a group. Okay. I'm sure you already got that from the motivation introduction that I introduced. Okay. So in fact, in some texts, you have only three conditions. You will have a sentence like, suppose that G is a set and star is a binary operation. If these three conditions hold: associativity, an identity element, an inverse element for every element. If these three conditions hold, then G together with star is called a group. So you need, so pay attention now, you need all these three to be present, okay? To be present in order for a structure to be called a group. Otherwise, you can't say it is a group. Okay, so if you say something is a group, it means that the binary operation, okay, that is associated with it, all right, is associative. And then within the set, you can identify an identity element. The E here is called an identity element. And also there is what is called the inverse of every element. Now note that in the case of the identity and the inverse, both of these operations are important. They must exist. I should be able to take X star E as well as E star X to get back X for every X, okay? And then the same thing for the inverse. Apart from that, I don't need this commutativity. Commutativity only applies in the case of the identity and in the case of the inverse. Otherwise, I don't need the operation star to be commutative in general. Okay, it doesn't have to be commutative. The most important thing is associativity. And you saw that when we looked at the simple examples. Okay, well, this definition shows that if G is a group, G can never be empty, because for it to be a group, there has to be an element called the identity element E in it. So G can never be empty. Okay, E, of course, you've seen this already, is the identity element, and X inverse here is called the inverse of X. Okay, so basically that is a group. When you hear a group, this is what it means. So what well, here, okay, so remember I just said that you don't need the operation, the binary operation, to be commutative, right? So in addition to all these conditions, if the operation is also commutative, then the group has a special name. It's called abelian group. Okay, so an abelian group is a group for which the binary operation is commutative. Okay, so that's the definition of an abelian group. Okay, great. Now, so what are some examples of groups and what are some sets that are not groups? Okay, so let's look at that. That will clarify what the group is. So the set of positive integers here, Z plus here, under addition, okay, it's not a group. Remember, I can't say that the set of positive integers is not a group. I need to specify the binary operation as well. The two must go together. I made this point earlier, okay? So Z plus under addition is not a group, okay? Why is it not a group? Well, it's not a group because remember that for a structure to be qualified, to qualify as a group, all these three, right? II to IV here must be present in the set. Well, this is because there is no identity element, okay, in the set Z plus under this operation. You see that? Let me probably pull out my let me see, bring up my input panel here and try to do something. Input. So the set of let me clear this. Okay, so G here, we want to look at the set Z plus, right? The set of positive integers under addition. So I have positive integers, right? I have z plus, right? So clear this, z plus, okay? Is the set of positive integers. So from 1, 2, 3, 4, and so on, right? That's the set. And then we want to consider addition, okay? So that's the operation. Well, so this set together with addition, will it be a group? That is the question. And we are saying it's not a group because there is no identity element. In other words, there has to be an element such that if I pick 2, for instance, and add it right to that element, I should get back 2. Okay, I need an element. Actually, let me do this to make it consistent with what you've seen before. I need, oops, where are you? It's gone. So let me bring it back. The input panel. Okay, it's back. All right, great. So z here is equal to z plus, okay, is the set if 1, 2, 3, 4, and so on, right? It's infinite. And then I'm considering addition, okay? For this to be a group, there has to be an identity element, an element such that if I take, let's say 2 and add it to that element, I should get 2 back. Well, the only element for which when I add 2, I get it back is 0, but 0 is not, okay? 0 is not part of this set, z plus. Because of that, this guy here, z plus with this guy here is not equal to a group, okay? My thing is not coming up well, but you get what I mean, right? It's not a group because we cannot find an identity element. I can pick 2, I can pick 3, there is no identity element. And that is enough to disqualify this structure here, z plus together with plus as a group. It's not a group, okay? You can look at inverse, but it's not necessary in this case, right? We know that there is no identity, so it's not a group, okay? Okay, good. So that is what we just said here. Okay. Example 4. Well, suppose that there's 0, right? In this case, there was no 0. Suppose that I define a new set, which is the set of positive integers in addition, union 0, in addition to 0. Okay. So this will be the set where you have 0, you have 1, you have 2, 3, right? And so on. Under the operation addition. Well, question is, if I take this set with addition, is it a group? Okay, it's not a group. Well, this time there is an identity element, which is 0, right? If I take any element here, okay, and I add it to 0, I get the element back. So there is an identity. So that is fine. But there is no inverse. You see that? If I take 2, I need an element here so that if I add that element, okay, let's call it x. If I add it to 2, I'll get the identity element back. The identity is 0, right? The identity element here in the set is 0, if you like. But I need an element x such that when I add, let's say 2 to it, I get 0. Well, there is no such element. The only element that will give me 0 here is -2, but -2 is not part of this set, okay? Because of that, this together with addition is not a binary operation. Sorry, it's not a group, okay? So that gives you some idea of how you determine, all right? In the first case, we eliminated the structure based on the fact that there's no identity and there was no inverse either, actually, right? And then in this case, even if you have an identity, we don't have an inverse for any element. Okay, and so there is no so this together with addition is not a group. Okay, good. So you're probably asking, so which set is a group? Well, if you take this set, the set of all integers, right? The set of integers, the set of rational numbers, the set of real numbers, set of complex numbers under addition, that's right. That is actually not just a group, abelian group. Okay, because commutativity holds. All right. So these guys, these sets under addition are abelian groups. You can show that if I take any element, any integer, all right, I will have an identity, right, which is 0. I'll have the inverse of every number. If I take 2, the inverse is -2, right? So I'll always have the inverse of a number in there, such that if I add it, I get 0. So that's fine. Also, this set together with addition is associative. If I take any 3 elements and group them, combine them, under addition, I'll always get the same thing, right? Remember associativity. Therefore, these guys together with addition is an abelian group. There is commutativity, that is why it's abelian. Good. Here is an example, which is probably not so familiar. So this, okay, I'll bring my input again. Anil, where are you? Okay, so let's see. Input panel, math input. Okay, it's going somewhere. Close this. Let me see, close this guy. Okay, all right, good. So let me see my, if my math, okay, math input panel is here. So you clear this. So this example, this structure here, we will show that it's a group, right? This means additive group of integers modulo n. This is from modulo arithmetic. All right. So so I take the set of integers. Okay. I take the set of integers. Let me just consider just the positive ones to illustrate what this is, right? Let's take 0, 1, 2, 3, 4, and so on, right? Well, if you do Z1, okay, Z1, what you mean is that if you take any integer and divide by 1, the remainder is what you get, is the answer, right? So if I take any integer, well, you can add the negative ones, all right? And I divide by 1, the remainder will be 0. So Z1 here has only 0 as its element, okay? That is why Z1 here is 0. Because if I take every integer, divide by 1, the remainder is 0, okay? Z2 means you take every integer, divide by 2, the remainder. So the remainder will either be a 0 or 1. That is why we have this. You see that? Here. So if I take, let me do this. If I take Z2, okay, its elements, if I take 0, for instance, divided by 2, the remainder will be 0 if you like. If I take 1, the remainder is still 0. If I take 2, the remainder is 0, right? If you take 3 and divide by 2, the remainder will be 1. If you take 4, divide by 2, the remainder is 0, so I have 0 there. If you take 5 divided by 2, the remainder is 1. So for all integers, your remainder will either be a 0 or 1. So Z2 here has 2 elements, okay? Z3 has 3 elements. Of course, you can guess, right? It will be 0, 1, and 2, okay? Erase this. This looks ugly. 2, okay? Then, of course, you can generalize this, right? Zn will be equal to the set 0, 1, 2, up to what? Up to n minus 1, right? You see that? It's up to n minus 1. When it's 1, we end with 0. When it's 2, we end with the 1. When it's 3, we end with the 2. So it's n, we end with the n minus 1, right? Good. So this set, all right, a set of additive, this is a set of additive group of integers modulo 1. So the set of integers modulo n under addition is a group. That's what we're saying. In other words, you can show that if you take, for instance, this one, take any elements, you can show there's associativity. You can show, what is it called, that there is an identity element and that there is an inverse as well, right? So I'll just do Z2 and show you that that is the case, okay? I'll show you a few of them. So if you just take Z2, let's clear this. If you just take Z2, right, which has elements 0 and 1, right? Okay, so the thing is that this is a group. And the point is 0 is the identity element, right? If I take any two elements here and I add them to 0, I will always get 0. If I take 1 plus 0, the result will be 1. All right? Of course, 1 plus 0 is 1. If you divide by 2, the remainder is 0. Actually, this is 0. Okay? And 0 is an element here. If I take, you can use 0 and 0, you get 0. You can do 1 and 1. All right. Well, we can do 1 and 1. 1 and 1. Well, 1 and 1 will still give you 0, right? 1 plus 1 is 2. 2 divided by 2, the remainder is 0. You get 0, right? So in fact, the element, it's its own inverse. Do you see that? 0 is the identity element. And if I take 1, the inverse of 1 under modulo 2 here is still 1. Because if I add 1 to 1, I get 0, which is the identity. Okay? So I have an identity. I have an inverse. Okay, you can show that it's associative. If I do 0, for instance, plus 1, and then, this is weird. Okay, if I take 0 plus 1, let's say plus 1, okay, and I do 0 plus, in brackets, 1 plus 1, I should get the same thing, right? 0 plus 1 under modulo 2 will give me, well, this is a 1, right? 1 plus 1 is 2, but 2 under modulo 2 is 0, right? 1 plus 1 here is 2. Under modulo 2, that is 0. 0 plus 0 is 0. So they give me the same thing, right? You can test it for different combinations of numbers. You can use 1, 1, 1. You will see that it's associative. So associativity, identity, inverse, all present. So this set here, all right? This structure here is a group. Okay. Now the set Z plus under multiplication is not a group. Why? Because there is no identity element. See, there is an identity which is 1, okay, but there is no inverse. For instance, if I take 5, right, under multiplication, the inverse of 5 here will be, if you like, 1 over 5, but 1 over 5 is not a positive integer, right? It's a rational number. Therefore, Z plus together with the multiplication is not a group. All right? Okay, good. Now the set R plus and Q plus under multiplication are abelian groups, okay? So you can show that if I take any positive real number, and I will have an identity, which is under multiplication, that identity will be 1. The inverse will be the reciprocal of the number, right? So I have an inverse for every number. Positive, remember, these are positive real numbers. You can show that multiplication is associative under positive real numbers. So all three are satisfied, therefore it's a group. This, you can do the same for this. Then finally, we also have a special, this is another example of groups. They are called permutation groups, all right? But I'm going to defer treatment of permutation groups later after we've looked at the theorems on groups, okay? So we'll come back to this. We'll come we'll come back to permutation groups later on. So I'm going to stop this now. And then when I come back, I'm going to start looking at some theorems, all right, on groups, like uniqueness of an identity, uniqueness of inverse, some cancellation laws, one-sided identity and one-sided inverses, okay? So we'll look at this in our next, in the next video, okay? Great. So go over the stuff that we have done now and try to understand If you don't, just let me know. Okay.